In this unit, we are going to apply the determinants to the calculation of inverse matrices. We are going to do it by applying the method known as the method of the adjoints. For this, we have to remember how determinants are calculated for matrices of any size, and also to know the concept of inverse matrix, obviously. So first, we remember the determinant of a square matrix, a number associated with the matrix, which helps us to know if the inverse matrix has 1 or not, depending on the value of the determinant, whether it is 0 or not. To calculate inverse matrices, which is what we are going to see in this unit, it can also help us to see the range of a matrix. We will normally denote for a square matrix A, the determinant with the expression of dA, or this expression that you have here on the screen, so that it is more comfortable to denote. So, given a square matrix A, the first thing we define is the complementary submatrix of an element of that matrix. The square matrix has n rows and n columns, so we choose an element a sub ij, and we define the complementary submatrix of that element to its ij as the matrix that is obtained by suppressing the row I and the column j in the matrix A. Exactly the row and the column that occupies the element in question. For example, for this matrix, if I select this element, the 3 here, which is the element of row 1, column 2, what is the complementary submatrix associated with the element S3? That element of row 1, column 2, well, the one that results of eliminating the row 1 and column 2. If I eliminate row 1 and column 2, what I have left is 0, 3 minus 1, 3, a matrix of 1 order lower, 2 times 2. Since I eliminated a row and a column, well, that's what we call a complementary submatrix. Well, if this is its complementary submatrix that is also square, we calculate the determinant, we obtain what is known as the minor complementary. The smallest complementary element to its A, sub ij, is the determinant of the complementary submatrix of that element, and it will be denoted by this expression. For example, in the previous case, for this 3, the minor complementary of that 3 is the determinant of this submatrix. 0, 3 minus 1. 3, which is exactly 3. It is a number because it is a determinant. Well, if we also add a sign to that number, we obtain what is called the adjoint of the element A sub ij. It is the number that results from adding a sign to the minor complementary. And that sign will depend on the position that the element A sub ij occupies. That is, it will depend on minus 1 raised to I plus j, where ij is the position of that element. For example, for the 3, which we have been working on all the time, the complementary submatrix was this, the minor complementary was 3, and the adjoint of that element, since 1 plus 2 is 3 minus 1 raised to 3, is a minus sign, then it is minus 3. It is not exactly the determinant, but it has changed the sign by the position that the element occupies in question. Well, that is what we call the adjoint of an element. Well, we are going to use the adjoint concept to calculate inverse matrices. Given a square matrix that is regular, that is, that it has an inverse, we know that it will have an inverse, sure if its determinant is different from 0. In that case, we can make sure that the matrix is invertible, and we can also calculate its inverse in this way, as 1 divided by the determinant of the matrix, times a matrix in which in each row and column I am putting the adjoint of the element in question. For example, in the first row, in the first column, I will put the addition of the element 1, 1. In the first row, in the second column, I will put the adjoint of the element 2, 1. Here we change the indexes. In the first row, in the column n, I will put the addition of the element n, 1. And so we subsequently build a matrix formed by the additions, which is exactly the inverse of the matrix A. This is the method of calculating inverses by adjoints. Let's see it with an example. If we want to calculate the inverse of this matrix, the first thing we are going to do is to know if it has an inverse or not. Because they tell us if it exists, it could be that the matrix was not invertible. So, what is the first thing we have to do? Well, see if the determinant is null or not. If we calculate the determinant, in this case it comes out that it is worth 3, applying the rule of Saros, which is different from 0, with which we are sure that A, it's invertible, and that therefore the inverse exists. Then, let's calculate it by applying this method. So the first thing we know is that the inverse is going to be 1 divided by the determinant, 1 divided by 3. Multiplied by a matrix that each of its elements are adjoints of the elements of the matrix A. Well, let's start. What will be the A, 1, 1, this one here? this one here will be the adjoint of the element 1, 1. The adjoint of the element 1, 1, remember that we suppress row 1 and column 1 and we build a determinant. And we put that determinant as a sign. That sign depends on the position. As 1 plus 1 is 2, minus 1 raised to 2 is 1, then it is exactly the determinant sign, it is minus 1. Let's continue with the next. If we want to calculate the A21 is the adjoint of the element of row 2, column 1. Then I eliminate row 2 and column 1, and I have 1, 1, 4, 3. As 2 plus 1 is uneven, minus 1 raised to 3 is minus 1, then I will have to add a minus to that determinant. Therefore, the result, in this case, if this determinant is minus 1, when multiplying by minus, I have 1, and so on with all the others. If I now substitute, then here I will have minus 1, here I will have 1, and here all the others that I have calculated with this method that we have seen, with which we already have the value of the inverse matrix of A. We can check that. A times A inverse, which is the expression here, gives us exactly the unit matrix 3 by 3. And we have calculated its inverse like this. Well, we have seen that it is the adjoint of an element and how to use them, the adjoints, to calculate inverse matrices.